What's up, everybody? Welcome to a quick little chemistry video about electron configuration, specifically a type of electron configuration known as abbreviated electron configuration, as well as orbital notation, and finally a little bit of Lewis dot diagrams. So if you remember back to yesterday in class, or the last time we had class, or the last notes we did, whatever you are remembering, we talked about doing electron configurations. And for something like silver, for example, we got an answer that was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. And it took us a little bit of time. We just used the periodic table and filled it out as we went along, starting up at hydrogen and going to whatever element we were looking for. And then after that, we saw this big, long written out thing. And the question you might be asking yourself is, do I have to write the entire electron configuration? And in the last class, had you asked that, I would have said yes, just to kind of learn what it all means. But really, no, you don't. There's something called the abbreviated electron configuration. And what the abbreviated electron configuration does is it looks at the noble gases, this last column on the table here. The noble gases have a completely filled shell. They are unreactive. And even in elements that come in the row after the noble gases, they do not lose those inner electrons that they share with the noble gas from the row above them. So what we do is we put the noble gas in brackets. And we say, okay, it has all these electrons from this noble gas, which it's never going to use in bonding. And then we just pick off where that left off. So if we're doing, say, phosphorus right here, right? Phosphorus has all the electrons in neon, which would be 1s2, 2s2, 2p6. It has all those, which it doesn't use in bonding, and then phosphorus would also have the 3s2 and the 3p3 to round out its electron configuration. So we're going to do an example of one of the larger ones, actually a couple of larger ones, and just see how this works and see how it is quite simpler and quite the big time saver. We're going to do this for bismuth and for strontium. Alright, let me shrink or put this periodic table somewhere where we can see it. There we go. And we are going to start with bismuth. And bismuth is right here. I'm highlighting it in yellow. Alright, what we can see is that bismuth is in that 6p block. Alright. So we have to worry about counting in 6p. To do abbreviated electron configuration, though, what I do is I start by drawing brackets. And inside those brackets, I put whatever noble gas is in the row above bismuth. So here's bismuth right here. I go up a row and all the way to the end, and I see xenon is the noble gas in the row above bismuth. So I go in and I put X E in brackets. And this means it has all the electrons, all of those electrons in xenon. And then I continue to do what I do next time. It's kind of like a cheat code to kind of jump ahead in our game of Chemical Candyland here. It's like you just pulled the ice cream princess card, and you get to zoom towards the end of the game to where the ice cream cone is on the Candyland board. All right, so if I'm going with that, here's Xenon. After Xenon comes Cesium. Cesium is in 6S. So I go right in my 6S. There are the 2 elements in 6S, so I get a little 2 up top there. After 6S, it looks like I want to jump to 5Ds, but see, I have this box with the asterisk. This means I have to jump down to the F blocks. I don't want to forget those little F elements that are down there. All right, and I get the first row, which is the 4F. So all these elements have electrons in that 4F orbital. So they're really easy to miss. All right, so you don't want to miss these F elements at all. So after 6S, I jump down here to 4F, and I make sure I get all these little FN elements down here. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 4F elements down there. So I'm in 4F, and there were 14 elements. After this 4F row, now I can jump back up. All right, and the other thing I could do, I could follow the atomic numbers. I go 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70. Next one would be 71, which is this group right here, which is that 5D group. And that 5D group has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. 5D10. Now I'm in 6P. Right here, now I'm in 6P, and I got to count over to bismuth. We got 6P. It is the 1, 2, third element over. And there is my abbreviated electron configuration for bismuth. Contains everything in XE. All right, so I save everything that comes before 6S, which is 1S all the way through 5P. I save all that writing, all that time, by skipping ahead to XE. All right, I'm going to go in and erase my periodic table here so that I can draw all over it again. I'm going to go do the next one. We're going to do strontium. Strontium right there. Make it nice and green. All right. So, strontium. First thing I do, I go up a row and all the way to the end. I see that Kr is at the end of the row above strontium. So it means it has every single electron for Kr. Alright, so Kr is in the row above. I put Kr in brackets. After my Kr is in the brackets, I can start going a little further. Oh, I got zoomed out somehow. Hold on a second here. Right now we're zoomed back in. So my Kr's in brackets. Alright. I have to go after Kr. The next orbital right here, the next little orbital in parentheses is 5S. Alright, the 5 6s. And strontium is the second element in 5s, and my abbreviated configuration for strontium is Kr in brackets 5s2. And that is all you have to do for abbreviated electron configuration. All right, we're going to move on to the second slide. These are called orbital filling diagrams. Orbital filling diagrams come right from abbreviated electron configurations. So what we do with these is we use the abbreviated electron configurations and we draw in the orbitals. And we draw them as either boxes or lines, and then we put the electrons in. And anytime we see an s orbital, we draw 1 box. A p orbital, we draw 3 boxes. D orbitals, we draw 5. F orbitals, we draw 7. One thing to remember, right? This is half as many elements in that block of a table. Right? S block has 2 elements, we draw 1 box. Half of 2 is 1. P block has 6 elements, half of 6 is 3. D block, half of 10 is 5. F block, half of 10 is 7. Right? Each block can hold 2 electrons. We represent these electrons as an up arrow and then a down arrow, because they actually spin in other directions. That's how these 2 negatively charged things can be occupying the same living space, pretty much, is that they spin in opposite directions, and so they kind of avoid each other that way. And finally, any boxes of the same level half fill each other first. So if there's 5 or 7 boxes available, you put 1 electron in each of the boxes before you team those electrons up. This would happen with 3 boxes as well. All right, if we think back, we're going to go do one of these for bismuth. If we think back to bismuth, what we have going on, there's a periodic table. I'll shrink it down a little bit there. All right, if you remember, we did bismuth on the last page. Bismuth right there. Bismuth had itself an electron configuration of, or abbreviated configuration of xenon in brackets 6s2, 4f14, (5d10), 6p3. So now what I have to do is I have to go in and I have to draw a little box for all of those. So I have a 6s box. I need 7 4f boxes. 1, 2, 3, 4, 5, 6, 7. 5 D boxes. And 3 P boxes. So I got 6S, 4F, 5 D boxes, and the 6 P boxes. All right. So I have my orbitals drawn in now. I'm going to actually do a little more of a zoom in here. I don't really need my periodic table for this. I would need it if I needed to come up with the electron configuration. I kind of took a little shortcut for bismuth there because we did it before. And now in the boxes, what I'm going to do is I'm going to put in electrons. And these electrons are just the exponents on the little letters. So 6s has an exponent of 2. I got to put in 2 arrows. I get an up and a down for the 2 electrons. F, I have to put in 14 arrows. Each box gets 1, 3, 4, 5, 6, 7. All right, now that the boxes are half full, I can put in the other 7, 8, 9, 8, 9, 10, 11, 12, 13. There's my 14 4f electrons. The d orbital has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Doesn't matter which order I fill the boxes as long as I half fill them first. And then 6p3, well, there's 3 boxes. Each box gets 1 electron. And there we go. That is an orbital filling diagram. All right, you're just drawing in boxes and arrows based on your abbreviated electron configuration. Okay, our final slide is on Lewis dot diagrams, and this is the last little thing we need to know. And these are really pretty easy. We use our electron configuration and our orbital notation to draw dots. And we draw dots equal to the highest energy level. It's the highest number in front of any of the letters. What you'll see is that we're talking about only the S and P orbitals. And that tells us how many dots we draw around the symbol. You will never, ever, ever draw more than 8 dots around an element. There are a maximum of 2 s electrons and a maximum of 6 p electrons. By my math, 2 plus 6 is 8. You should never have more than 8 electrons in the s and p combined. So you should never have more than 8 dots. Some of the bigger questions, or more point-heavy questions, that come up from this unit involve doing these 3 things. Doing an abbreviated electron configuration, an orbital filling diagram, and the Lewis dot. All right, in this case, we are going to do this for the element selenium, which is Se. I am going to grab myself a periodic table. Here's a periodic table. I'll actually make this pretty big here so we can really see it. All right, I'm trying to do all these for Se, selenium, element number 34, right here highlighted in red. First thing I do is I find selenium, I go to the row above, and I find the noble gas. So the row above selenium ends in argon, which means I'm going to start off with Ar in brackets. So I'm starting off right here at argon. After argon comes 4s, and there are 2 elements in 4s, so 4s, 2. Then comes 3d, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in 3d. I then hit 4p, and then 1, 2, 3, 4 elements in 4p until I'm at selenium. So there's my abbreviated electron configuration. Second thing I need to do is the orbital filling diagram. So I draw in that 4s box. The 5 3D boxes. And the 3 4p boxes. Now I'm going to go in, I'm switch my color up a little bit, and I got to put in the number of electrons. 4s has 2 electrons, it gets an up and a down. 3d has the 10 electrons, it gets 10 arrows, 1, 2, 3, 4, 5, half fill first, 6, 7, 8, 9, 10. 4p has 4 electrons, half filling puts 1 in each box, and now this 4th electron can go in any of the 3 boxes. It does not matter. As long as you put it in one of those 3 boxes, and there's a total of 4 arrows, everything is right. So I'm going to put it in the middle box for fun stuffs. All right, so there is my orbital filling diagram. The last part is my Lewis dot. For a Lewis dot, I E, which is the symbol of selenium. After I write that symbol for SE, I need to go in and I look. I am going to pull out only the high energy levels. So the high energy levels are the 4s. So I ignore the 3D elements. And so there's a 4s2, 4p4. I take that 2 and a 4, I add them together. 2 plus 4, where I come from, is 6. So I got to put 6 dots around selenium. And I can do 2 dots per side. I'm just looking for you to do 6 dots. The best way to do it is to put the first 2 dots together and then do 1 dot at a time. But I'm not going to watch your dots. I'm not worried too much. I'm looking for 6 dots. So 1, 2, 3, 4, 5, 6 dots. And that's it. That means selenium has 6 valence electrons. All right, the other thing that this all means is that since we only look at S and P electrons, any D block element, remember the D block is over here, big, thick D block in the middle, or the little F block elements at the bottom, those F block elements also have electrons in the F block. The D block elements have electrons in the D block. We don't count F and D's when we do the dots. We only count S's and P's. Since D and F come before P, they all only have 2 dots. So most of the table has 2 dots. And then you're just looking at how many S's and P's are in the abbreviated electron configuration. All right, that is all. The homework is up on Schoology. So it's up on Schoology. Orbital filling homework. I think it's homework 7.2. It's just a handful to work on. You should be able to do them, get them done, submit it real good. We have a little lab on the long day that is coming up. And after that, we can talk more about this stuff. We can do some more examples just to clear anything up. So thank you, and I hope you had a good time talking about abbreviated electron configuration, orbital notation, and Lewis dot diagrams.